Today's guest speaker is Michael Pack, who is director of the Center for Advanced Transportation Technology Laboratory. He came all the way from Maryland, so let's give him a round of applause.
Thanks, Ruben. So today I'm going to be talking to you about data visualization, trajectory data, probe-based data, and some other data sources, and how we at the CATT Lab at the University of Maryland are integrating that data and trying to make it easier for you all to do research on that. So let's see. At the CATT Lab, which is the Center for Advanced Transportation Technology at the University of Maryland, we have about 50 full-time professional software developers and 20 to 30 student software developers and transportation students and even artists and whatnot, working to go out and collect any and all data that we can possibly find that has any sort of relevance to the transportation system. We grab that data from agencies and the private sector, and we suck it down into a system called RITIS. RITIS stands for the Regional Integrated Transportation Information System. And once we have that data, we fuse it together, and then we make it available back to real-time operations folks and applications and planners and researchers for doing whatever it is they need or want to do with that data. And so this is a screenshot that I took, actually I guess this is a couple of years ago now, of a real-time snapshot of what's going on in the United States. You can see at the time there was some sort of a hurricane going in Florida. So here's a vehicle that was on fire up here in, I guess, South Carolina. Some fatal accidents, people calling 911. There's all sorts of other stuff that's going on. And instead of talking about a picture, I'll just show you the real system real quick before we move on. Here we go. So here's a map of what's going on around the country right now. I'll zoom into like the East Coast area. All of the roads are color-coded based on speed data that we're getting from the tracking of cellular phones. So if anyone is out on the road driving and they're using their cell phone to navigate, we are collecting that data. And so we know essentially how fast people are driving out there. I'm not technically color coding the roads based on speed alone, as if I was to do that, then most of the East Coast would look red all the time. So instead, we maintain a historical archive of what the speeds are like on a Tuesday at 12:34 p.m. And then we recolor the roads based on whether they're performing at expected conditions or not. And then all this other stuff that's going on are collisions, roadwork, disabled vehicles. I have this for around 25 states right now. I have probe data for the entire country. But it's not just there's a thing happening at a particular location. Each one of these events has a lot more data behind it that we're collecting and fusing from different sources. So this is a real picture of a real incident that happened in Maryland, I-95 North at Maryland 32. This is an example of all the data we're collecting just for one collision. The red line here is the start of an incident at 12:30. That's 1 o'clock, 1:30, 2 o'clock, 2:30, 2:43 p.m. is when the incident ended. And then all this other stuff that's going on, these are temporal events that happened during this particular collision, which involved a tractor-trailer truck and a pickup truck. So these little diamonds that are popping up here on this section, these represent agencies and when they were notified about this incident. So for example, a tow truck was notified a little after 1 o'clock in the afternoon. Then the dashed line that follows it is when the tow truck was driving to the scene. And then the solid line is when the tow truck was actually on the scene and doing something. So we have that for the tow truck, accident investigator, police, fire department, DOT units, all sorts of other groups up there as well. Then below that, we have the lane status and how that's changing over time. This is the northbound direction. This is the southbound direction. When the incident first started, the right lane and the right shoulder were blocked. Then you move forward in time, all of a sudden all of the northbound lanes get blocked because that's when the fire department arrived on the scene. Fire department loves to block all the lanes when they pull up to an incident. And then we move forward in time, all of a sudden all of the southbound lanes also get blocked. And they get blocked to make way for this medevac helicopter to land and do whatever they do on the scene. And then all the other lanes remain closed until the end of the incident when the accident investigator departs, and that's when the right shoulder remains blocked for the tow truck and the police. And below that, these little lines right here represent different dynamic message signs that were out on the roadway and what was being posted on the sign and where the beacons turned on. And then here, this is the queue that's building up behind the incident. And this queue is being measured from the probe data that we're getting from NREX here, TomTom, Google, Waze, all those different groups. So that's the location of the incident, that black line. That's 5, 10, 15 miles behind the scene. As these lanes remain blocked, the queue backs up further and further and further until all the lanes open. And even after the lanes open, the queue's still backed up about 7 miles. It takes another 45 minutes or so before the queue starts to dissipate and it's propagating backwards and traffic starts to return to normal. So that is a real incident, and you can actually go into the system and you could find a collision in here and bring it up, and you could look at a real live timeline to see what's going on at the scene of that particular incident. So here's one where there's 3 responders on the scene right now. I'll click that button, and it's grabbing all the data, and it's generating the timeline for who's on the scene right now. So we have that type of information. We also have transit data. So where are the buses? Where are the trains? Where are the subways? We also have radio communications for the entire country. So you're going to see these little red dots pop up all over the place. That's the police, the fire, the EMS, the air traffic control. That's all of their communications. We can actually click on one. Nassau County. There's all the different responders in Nassau County. And in a second, you're going to start to hear some audio coming perhaps from my computer over there. These will turn green, and you'll actually be able to hear people speaking and dispatching in real time. All of that now is getting archived for the entire country, and we're adding that up on top of the incident timeline that I showed you earlier. So there's just a lot of data that is coming in, and that's not even half of it. There's tons of other sources that are up there as well. So let me go back into the presentation. There we go. So just showing you more pops. We have road weather data as well for the entire country, so you can get the air temperature, the surface temperature of the pavement, whether or not there's any salt that's been deployed. You can actually measure the salinity content and the visibility around the country. I showed you the timeline already, so we'll skip over this. We also have fleet vehicle locations. So the first responders, the Department of Transportation maintenance vehicles, some of the agencies give us the GPS coordinates in real time of all these vehicles. And in some cases, we actually have the real-time video coming off of the vehicle back to us in our center. So like dash cam video, you can actually see what the driver is seeing as they're driving down the roadway. And then you can go back in time and see where people were and where they're moving about. I mentioned the transit. We also have real-time transit for several hundred transit agencies around the U.S. And we're archiving all of the on-time performance metrics and the locations of vehicles and passenger counts and fare collection, depending on whether or not the agency has that to offer. And we're also pulling in weigh and motion data. So there are many sensors scattered throughout the country that are actually weighing vehicles as they're driving down the roadway, not pulling off to a weigh station, but as they're driving down the roadway. And in real time, we're taking a picture of each vehicle that drives past these locations and then measuring the axle spacing, weighing how much each axle is, all sorts of stuff. And so that's being archived as well. So how much data are we talking about? Well, right now, traffic collisions and events, I'm getting around 220,000 events per day, crashes or disabled vehicles or what have you. And then there are sensors that are out there counting cars, doing speed measurements, getting around 85 million measurements per day across the United States from sensors. Then the probe vehicle data, that's the cell phones that I talked to you about earlier, if you're using your navigation system to drive around. 7.5 billion, with a B, measurements per day. And then there's real-time video data, there's weather data, radio, and I'm not keeping good stats on how much of that we're collecting, but it's even bigger. And now we're starting to work towards connecting autonomous vehicles data in a couple of states as well. So the point is, the data is getting bigger and bigger and bigger. And these are all big numbers, and as humans, we all struggle to comprehend big numbers in general. Have any of you ever read a book called Enumeracy? It's a really short book. It's available on Amazon. Pick it up. If you're going to be working with numbers, and assuming all of you will because you're engineering students, pick up this book and give it a read. It helps explain how difficult it is for us to understand these numbers. So here's an illustration. If I had a stack of $100 bills, that's how big the stack would need to be to reach $10,000. This is a relatable example, right? We all see the stack of $10,000. So think for a second, how big would that stack be now to go up to $1 million? Just think, how big do you think that would be? There's what $1 million would look like. Now let's take it to the next level. How big would that stack look if it was $1 billion? Just think about that. There's $1 billion. And now think about $1 trillion. That's what $1 trillion would look like. Now, for me, it's difficult to understand the concept of million versus billion versus trillion. My research budget isn't that big yet. But a trillion is a really, really big number. So working with data, especially really, really large data sets, can be particularly intimidating. Not just for us, engineers that supposedly understand numbers and know how to work with it, but also our clients, Department of Transportation staff, the public. At some point in time, you're going to have to justify the work that you're doing to the public, and you better be able to do that in a way that's going to mean something to the average citizen. So at the CATT Lab, we try very hard to build tools that make data more easily accessible, not just to engineers, but to the average Joe, but also easier to just use, easier to work with the data, easier to understand, and hopefully allowing for the data to actually provide some insights to whatever it is that you're working on, whatever problem it is that you're trying to solve. And we do that through data visualization. And we have a design mantra in the CATT Lab, and it's that we always want to provide you with an overview of your data set, and then we want to be able to give you the opportunity to zoom in on aspects of the data, filter, and then bring up details on demand. So always show you a picture, a big picture, and then zoom, filter, and then bring up details on demand. And you should all care about data visualization because data is probably the only thing you're going to work with moving forward. Data is the new oil. That's what everyone says, right? And you're going to have to be able to work with it. You have to be able to make sense of it and be able to present it to your managers and to the public and your clients and whatnot. And visualization is an effective way to do that because we all have incredible visual bandwidth. Your ability to perceive things in a picture will far outweigh your ability to perceive something in a spreadsheet. You're not going to remember a lot of what I talk about today, but you're probably going to remember a picture, something that I show you along the way. And when it comes to data, when you're looking at some sort of a chart or scatter plots or whatnot, your mind has the ability to distinguish color, size, distance relative to other things. These are things that you just pick up on intuitively really, really quickly. And your ability to retain that is incredible. So here we're gonna do a couple of experiments. First, I'm gonna tell you a story. It's just gonna be a narrative, and I want you to guess what the story is. So a broken family is reunited after the children enlist in the military, unaware that their father is a high-ranking official within the enemy force. Anyone think they know what story this might be? Don't say it, just raise your hand if you think you might know what this story is. We got one. All right. If I had just shown you a picture, you would have immediately known what this, hopefully you would have immediately known what this story was. This is an accurate description of the storyline for Star Wars. But the picture says a lot more and communicates a lot more quickly. Let's try another experiment. On the next slide, I want you to find the 3 countries with the largest values beside them. And I'm only going to give you 3 seconds for this. You ready? All right. Anyone have a guess?
Were there 3 different columns?
Yeah?
Do you know what to look at?
I don't know.
Luxembourg.
Luxembourg. So we have a guess. We got one brave soul. Anybody else? The point is it's hard to do. Let's actually go back and look. Where's Luxembourg? There's a reason why he's got a PhD. He's quick. Look at that. All right. But yes, you're right. Maybe I meant this column. Maybe I meant this column. Who knows?
I missed the USA.
That's right. That's right. All right. Good job. All right. Now let's try it again. On the next slide, find me the 3 countries with the largest values over them. Again, 3 seconds. You ready? All right. Anyone have a guess this time? India, China, U.S. I don't actually know what the answer is, but the fact that more of you guessed meant that more of you were actually able to interpret that picture more quickly. So India, China, the U.S., the dots are big. Maybe that's representative of a big number. Maybe color was representative of a big number. I don't actually know. This has something to do with fatalities, vehicle fatalities. But yeah, all right, so more of you had a guess, which means more of you were able to see some things. So what I'm going to do now is I'm going to jump in and I'm going to show you a few examples of some of the visualizations and the tools that we've created in the CATT Lab. Not all of them are perfect. Not all of them are going to tell a story exactly the way that you need it told, but hopefully it's going to help you to dive into the data a little bit easier. Some of these are incident analytics. I'm actually not going to talk about incident analytics today, but we do that. Some weather analytics, looking at traffic bottlenecks, congestion analytics. We won't touch on everything, but we'll see how much time we have. So the first thing I'm going to talk about is ping data, trajectory data from the private sector. Has anyone ever worked with trajectory data before? You might after I explain what it is. So trajectory data is really the underlying pings that all of the probe data providers are collecting to get speeds on the roadway. So Inrix here, TomTom, Google, they're giving you like an average speed on a segment of a roadway. Trajectory data goes deeper and it says a trip started here. And 30 seconds later it pinged here, and 30 seconds later it pinged here, and so on and so forth, and it ended its trip right here. So you're seeing the breadcrumb trail of it moving throughout its trip, including the origin and the destination. So that's one trip over there. Here's another trip over here on the right-hand side. This, come on. Let's go back. I'll click on this here. This is an animation of 1 day's worth of trajectory data in Washington, D.C. Again, each one of these little dots is representative of a vehicle or a person with a cell phone that's being tracked as they're moving throughout the system. It's a little hard to see, but everyone's mostly going into the city now. Now that it's the afternoon, you'll start to see people start to turn around and head back and go in the opposite direction. This is a data set that we got from the private sector. The company's name is Interix. So this ping data can be pretty big. Just 1 month's worth of trip data in Maryland is about almost 5 million trips. And the data can be messy as well. So look over here at this graphic right here. The orange dots, those are the pings, the raw ping data that we're getting from the data provider. What we have to do is we have to go and we have to snap these pings to a roadway and then tie the trip together into a route. Some of these pings, they might ping every second. Some of them might ping every 20 seconds. Some of them ping every minute or every 5 minutes. And theoretically, you can go a long distance in a couple of minutes. And so we need to be able to define what that route is, which turns did people make. So we go on and we do that ahead of time. And then we've built a set of tools that allow you to go in and then start to ask questions of the data. We've got this origin destination tool, a segment analysis tool, and a route analysis tool. The origin destination matrix tool is fairly simple. You essentially just go in and you define some geography. And it can be at the state level, at the county level, at a traffic analysis zone level, or a city block level, whatever you want. And you choose a date range and you click a couple of buttons and it just generates an origin destination matrix. Do any of you work with OD matrices right now? All right, cool. So you know what these things look like. This is interactive. I'm not doing a live demo of it, but this is interactive. You can go in and change the colors. You can filter this down based on whether or not you want trips, all trips throughout a year, or just trips on Tuesdays, Wednesdays, and Thursdays, or maybe you just want trips that began their trip between the hours of 8 a.m. and 9:15, or something like that. Or maybe you just want passenger vehicles, or maybe you want heavy vehicles. You can do that sort of filtering. And please ask me questions along the way. You don't have to wait till the end. And there's other visual analytics that we put in that allow you to look at how many trips are going from one location to another. It's just another way to look at an OD matrix in the round instead of in the rectangle. But my more favorite tool here is our segment analysis tool. This tool is a select link analysis tool. Has anyone ever done any select link analysis work before? It's essentially where you go in and you select a road that you want to analyze. So I can come in here, the segment analysis tool, and I would type in a road that I cared about. Typing I-270, that's an interstate that heads down into Washington, D.C. Here's Washington, D.C. down here in the lower right. This is I-270 coming down this direction. I don't want to study the entire road. I just want to look at a portion of this roadway in the southbound direction. I'm going to look at just the I-270 spur. That's one little segment. And what I want to do is I want to say for every trip that drove on this little stretch of roadway, where did the trips originate before they drove on this stretch? And then where did they go to? And the result is this. Let me zoom in. See that little green dot right there? That's the segment that I chose. And then all these little orangey blocks, those are where the trip started before they drove over the stretch of roadway. The darker the area, the more trips that originated from that particular zone. And so you can see there's trips way out here in Indiana, some trips way down here in Jacksonville. Most of the trips are kind of northwest because I chose a southbound road. We can zoom in a little bit and it should bring up more details. When I get in, you'll start to see some more of the colors that start to pop up. There's some darker zones, different areas. So that's origins. Now I'm going to go over and switch to destinations and click on that. It'll take it a second, and now it's going to then redraw all the roads and do the destinations instead. Come on. Where's my mouse? There it is. All right. So it's a little hard to see the blue. You see, a lot of the northwest trips are gone now because people are driving to the south. So now you see the destinations are down here. I'll zoom back in. And again, you'll start to see darker areas. You'll see some of the darker areas are out in where there's airports. There's an airport right there, so a lot of people are coming down this road, going to the airport. Others are coming and just staying in the city in this general area. So trying to make it, again, easier to work with these millions and millions of trips. Yes?
So this is, what time range is this covering?
This is I'm going to click up here. I think it's 2018 plus a random 4 months in 2015. So what happened is the state of Maryland wanted to test drive the data. So they bought a few months in 2015, and then the state just decided to buy all of 2018 and 2019, 2020. So we will get this data moving forward. But yeah, it's in 2015, it's February, June, October, and July. 2018, it's all the months. Yes.
So how do you separate trips? Like how do you
Great question. So right now, the data provider is saying anytime a vehicle stops, like turns its engine off or whatever, for longer than I think it's like 20 minutes or something like that, that's the end of a trip. That is not always the end of a trip. I mean, you can pull over and you can get McDonald's or something like that, and it can take you longer than 20 minutes. So we are now going in and trying to chain those together if they continue along on the route that we anticipate them going on. So that's still a work in progress. Now, what we do struggle with is for privacy concerns, at midnight, all the unique IDs of these trips completely switch over. And so we have to manually string those together at midnight if a trip was going through the midnight hours. And that's also why you don't see trips that drove across this road and went all the way to California. We only track people for a certain amount of time as they leave the state of Maryland. This data has actually been purchased by the New York City Department of Transportation. So if someone here wants to work with the New York City DOT, you can get access to the same type of data from them. Question?
So if I wanted to know the origins and destinations of trips that use Canal Street in Manhattan,
Yep.
I would go to DOT and they will have this data?
Yes, they will. Yeah. Now, to be fair, it is going to be a sample of all the trips. It won't be every single trip. Yeah.
And is the data collected from GPS devices, or are there vehicles in fleets that sell that information?
It's both. It's both. So there might be fleets that have telematics embedded in them, and that's being sold back to these aggregators, but it's also people using cell phones to navigate around. But it is definitely biased towards commercial vehicles right now. They're getting better at the passenger vehicles, but there's still definitely a bias.
Do you work with MPOs, Metropolitan Planning Organizations, provide data that they can use?
Yeah, so, well, my business model at the CATT Lab is I try to work with the states first, and once a state buys access to data, then all the MPOs within that state get access to it. There have been cases where MPOs have come to me directly, but
New York State bought anything?
the state has not, but the city has. Yeah. All right, let me go back into the slide deck here. So it is not complete yet, but we're now working on a route analysis tool that will allow you to study how people get from an origin to a destination. So this is the interface right here. You choose an origin. The origin could be an entire county, a cluster of counties, a traffic analysis zone, or a cluster of those, or a single segment on the roadway. And then the destination could be the same combination of those things. And so you would choose the origin destination, and then a date range and a time range, and it goes in and says, okay, well, for all the people that went from A to B, 70% of them took this route, 10% of them took this route, 5% took this route to get there. And it breaks down other things like the travel times between those. So you could choose a single route, and it would give you the average, the mean, the median travel time, the 25th, 75th percentile, the 5th and 95th percentiles for different times of the day. And the coolest thing, do I have a picture of it? Yes, the coolest thing is you can also choose 2 different date ranges to compare. So let's pretend you are getting ready to do a major construction project someplace. Well, after or as the construction project goes into effect, you could query a date range before the construction and after the construction, and it'll tell you between those date ranges, did people start to take a different route? Did a different route become more popular? So here I've chosen 2 different date ranges, and for each one of the routes in this list up here, it gives me the delta. So this particular route, route number 1, which is highlighted in green, decreased. So there were fewer people now taking that route. Route number 3 had pretty much no change. No one really changed there. Route number 2, this red route, saw an increase in traffic. So the Virginia Department of Transportation has been using this to look at the impacts of one of their new tolling policies that they have going into DC. Now these potentially really high variable tolling rates go up to $30 or $40 to travel this 5 or 10 mile stretch of roadway. They want to see now that tolling is in effect, are people getting off on the neighborhood streets and clogging the arterials and so on and so forth. This particular tool is not yet finished. It's probably got another few months before we've gone through all the testing. But yes.
So estimation here, you did this from the historical data, or you have your own method to estimate?
This is all based on historical data. We are not predicting what's going to change. That'd be awesome. We work together to solve that one. But yeah, this is just historical information. So this trajectory data has other applications, we believe. Has anyone heard of the SPAT challenge that's going on around the country right now? SPAT is signal, phasing, and timing. Federal government is encouraging agencies to go out and install better detection equipment at these signal controllers to get like 10 hertz measurements of stop bar detection and what the signal phasing and the timing is and whatnot. And the goal is to look at how many people are getting stopped on red, arrival on red, arrivals on green, so they can then retime the lights and manage the signals more appropriately. It's a great thing to do, but it's also a very expensive thing to do because, one, you have to run communications equipment, $1,000 per intersection to start collecting that type of information. That's the date range. And the tool goes out and it looks at every intersection and every turning movement in that region. And it's looking at these pings, these people moving around, and it says, okay, which of these intersections is performing worse? Which of them are performing better? How much user delay cost are we incurring at each one of these intersections? And it ranks them all. And then you can come in and you can click on an individual intersection, and just looking at these pings, we can count approximately how many people are getting through this particular light within 1 minute versus 1.5 minutes versus 2 minutes. And then boom, there's a jump at 3 minutes. Well, that's the signal switching over, right? So that's the next group of people. And there's a third group, a third phase, where people are getting stuck for over 5 minutes at this particular intersection. So is this as good as the 10 hertz measurements at the signal? No, not today, because we're not collecting data from every single vehicle that's out there. But it's still effective. It can still do a lot of cool stuff. And we're excited to see this rolled out before too long.
So,
Yes?
For New York City, isn't there like a comparison buildings also? How reliable are those?
The answer is probably, and I don't know. So for those who might be watching this live stream, the question is, in New York City, do we have the canyoning effect where the GPS doesn't work quite as well? My understanding is that that's getting better and better as time progresses, and I haven't directly studied to see if there's like a degradation in the signal, if we're getting less reliable data in New York. That hasn't been done yet. We did do one study to see how accurate the sample sizes were that we're getting from the provider, and we hired some helicopters to hover above part of the city, and we took thousands and thousands of pictures looking down from a really high altitude, and we tagged all the vehicles, and we looked to see where the origins and destinations were, and we compared what we were getting from the pictures to what we were getting from the data providers. It was not 100% accurate, but it was really, really close. It was pretty cool. All right, let's go on to another subject now. Thus far, I've been talking mainly about these pings, this trajectory data. Now we're going to go one level up to just basic probe data. So this is speeds, average speeds on a stretch of roadway for every minute of every day. We've built a whole analytics suite. Again, New York City DOT has access to this right now, so you all could probably have access to it as well. This tool allows you to go in and ask all sorts of cool questions about congestion in the city. The first thing I'll talk about is something called a bottleneck ranking tool. Let me go and show you this. All right. Bottleneck ranking tool is right here. If you click on the bottleneck ranking tool, it's going to open up a new window, and it's going to then allow me to go in and choose a state and a region. So I could come in and I could choose, all of New York. Where's New York? Oh, I gotta change over to Index. Where is it? Oh, there it is. So I don't actually have data for the entire state of New York. We just have the counties that make up the city. I don't remember what those are right now, so I'm going to do a Maryland example instead. But you would choose all the counties or zip codes or whatever, choose what road classes you wanted to study, you choose a date range, and you hit submit. And the result here, again, I ran a query for Maryland, DC, and Virginia, three regions there. I said for the month of January, tell me where the worst congested locations were in those three states, 2 states in the district. And it comes back looking at trillions and trillions of data points, and it gives me a ranked list up here of about 1,000 different locations. Tell me the worst location was I-95 South at Virginia 123. That's the location right there. That's the head of the bottleneck. That's the tail of the bottleneck working its way backwards. The lighter the tail is, the less frequently that part of the bottleneck was congested during the entire month. So it's really dark up here, which means pretty much every day this was congested and fewer days back here. It also gives me the average maximum queue length, so about 4 miles, average daily duration. So daily yes?
When you say bottleneck, is it from the red point all the way up there? Is one bottleneck?
Yes. Now, it's not every day that it goes all the way back here. This probably, well, that's about 10, it's probably about 15, 20 miles right there.
People do that every day.
Oh, yeah. People who live down here and work up here are not happy people. There's not a lot of happy people there anyway. But so that's the location. There's other stats that appear up there. One of them is that the average daily duration of this queue right here is 5 hours and 58 minutes. So it's a long duration. And for the entire month, this location was congested for a total of 7 days and 14 hours. And then this graphic over here is telling me when this location was messed up during the month of January. So it's a 24-hour clock. That's 12 a.m., 6 a.m., 12 p.m., and all the way back. So one revolution is 1 day. The innermost revolution is January 1st, then January 2nd, 3rd, 4th. January 31st is way out here. If there's color on the graphic, that's when this was messed up. So you can see it starts, reliably it starts around 2 p.m. and it continues around until 8:30 every single day. That's when it's congested. You can see the weekends in there. The little dots that are appearing, those are collisions or disabled vehicles or work zones that may have impacted that. Let me click on a different one. The next one on the list is I-495. So this is DC again, Beltway. You see this one's not nearly as bad. And you can see there's actually a weekday, weekend pattern right there. And the third one, I'll click on. I think this one has a morning pattern about it. Come on. It's a lot of data to load. The third one is I-495 counterclockwise. It's going to appear up here when it does. There we go. The Beltway. You see this one just happens in the morning. And see, it's got some outliers here in the afternoon, right? That's not normal. I can put my mouse over that. Now it tells me there's a disabled vehicle. So one crummy little disabled vehicle caused a massive bottleneck one day. And you can see there's other things up here. If you saw an event that you want to study, there's an injury incident, you could click on that injury incident, and now it's going to open up the timeline and show us how that particular incident was managed. Or you can click on the colored bar, and then when you do that, it's going to grab all of the data from that particular roadway for that particular day, and then it draws out what we call a congestion scan graphic. So it draws out the road with all the intersections along the way, and then it gives you the congestion on both sides of the roadway, and it overlays where the collisions and disabled vehicles are and all that sort of. There's a water main that broke down there. And there's another button you press that then goes in and computes how expensive the congestion is along the roadway. And expensive is in terms of user delay and user delay cost. So we look at the average value of time of Joe Public and then Joe Truck Driver. And Joe Truck Driver is going to be $100-something per hour. Public will be like $10, $20 per hour. Yes?
How do you measure delay?
Delay. So we give you the option of measuring it different ways. You can measure it just based on what the speed limit is, and if you're below the speed limit, you're delayed. You can set a threshold that says, I only want to compute delay if I'm 20 or 30 miles below the speed limit. Or you can go in and say something like, I want to know if the congestion today is worse than it would normally be, and then compute the delay based on that. And I think there's another option in there too.
You have measures of variance, or travel time variance, reliability?
Yes, yeah, those. So that's be like the planning time index and those measures. Yes, we can do that as well. I'll jump to that in just a second. But for the user delay cost, this graphic over the top, this is hour of day. This is day of week coming down right here. And each one of these squares has a dollar amount in it. So let's see, this one square right here says there was about $15,500 in user delay cost for this one little stretch of roadway. It gives me the person hours of delay, the vehicle hours of delay, and delay per vehicle mile traveled, and some other metrics. So we have a lot of agencies that are using this right now to justify projects. They use the bottleneck ranking tool to first identify where the biggest problems are. Then they'll go into the user delay cost tool to figure out how expensive the problem is. And then once they've gone and done the construction project or whatever remediation strategy there is, then they go back and they use the tools again, and they look to see if the user delay cost changed, if the bottleneck shrunk, all that sort of stuff. And that's really a good way to justify the public dollars that you're spending. Yes?
So what's the value of time that you use?
The question was, what's the value of time that we use? We have programmed into the system the national average value of time, which the Texas A&M Transportation Institute came up with. I imagine it is much lower than it ought to be for New York. So in the tool, there's a little box that pops up, and you just click on the box, and you can enter in whatever you think the value of time is for your region. But if you want the actual number, we could go in and look at it. Is it? Yes, you're right. So $17.9 per passenger vehicle, $100 for commercial vehicles.
So the hour.
Per hour, yes. Yes.
You track this in terms of trip length?
Ah, great question. He asked if we track this in terms of trip length. We have no idea what the trip length is for the majority of these trips. So that's why we give you another measure, which is delay per vehicle miles traveled. And then you can use that to then start to give individuals a sense of what their individual delay is. But yeah, we have no idea how long the trips really are.
But you can measure it, though. You have the data.
We have not gotten to the point where we're merging those two things together yet. Yeah, it would be good. We've really only just started to play with the actual trips data. That's a good point. You had asked about the reliability measures. We do have, let me change this up here. We do have the ability just for you to choose a corridor and then a starting location, and ending location on a corridor, and it will compute things like the speed over time and how that changes. The colored bars here, that's your 25th, 75th, and 5th, 95th percentiles. So essentially the best and the worst the travel time is ever going to be. But you can come down here and you can switch to planning time index, travel time index, buffer time. You can switch between all those different measures, display them pretty easily. Let's see, let's get back into the slide deck. We're starting to run out of time here. So I showed you the user delay cost table already, being able to just choose a corridor, set of corridors, and look at basic travel time measures. We have a really new tool. New York City hasn't bought into this yet, but this tool allows you to go in and look at signalized arterial performance measures. So imagine going in and being able to choose any corridor in the city and then choose a before time and an after time, before date range and after date range, and it would produce these cumulative distribution functions that let you see how many people were getting, what percentage of people were getting through this particular corridor in 10 minutes versus 20 minutes versus 30 minutes. So you really want this to be straight. If it's straight, up and down, it means pretty much everyone's getting through in the same amount of time. And if it's to the left, that means people are getting through in less time. So straight is reliability, left is travel time in general. So you compare the two, you put your mouse over individual segments, and it tells you whether each segment got better or worse after you did a retiming program or something like that. We have another tool that lets you choose all of the corridors in your state or your city, and then again a before and an after time period, and then it ranks every single corridor, and it tells you for all the corridors which ones improved reliability or which ones the reliability got worse or which ones the travel time got better or got worse. So it's ranking here a bunch of corridors in the state of Pennsylvania. There's all these normalized measures because these corridors are different lengths, right? So you have to normalize all these performance measures. And you essentially click on each one, and then it highlights this little graph down here. If the particular corridor has a green line that's going down to the left, that means both the travel time and the reliability have gotten better on that particular corridor. If it's going up and to the right, like these two are, both the travel time and the reliability got worse on those corridors. And if you've got yellow lines that go in either direction, that means maybe you got the travel times better, but the reliability got a whole lot worse, or vice versa. It depends on which way the line is going. So this one right now, only the Pennsylvania Department of Transportation is using this, but if you all wanted to explore it, we could give you access to data from another state to see if these are relevant. Let's go over a couple of real-world use cases. Pennsylvania Department of Transportation, where he was getting ready to do a $2 billion reconstruction project for I-95 going through the Philadelphia region. And they used our tools. It took them 10 minutes to go in and say, produce a graph that shows me what the speed travel times were in 2012 versus 2013 versus 2014. 13 and 14 is when they started to do the construction project. And they could see that the travel times got a little bit worse, not a whole lot worse, but the variability got a whole lot worse. So they're really messing with the reliability of people's trips here. And just this simple graphic, again, it took like 5 or 10 minutes, helped the Pennsylvania Department of Transportation to justify an increase in transit spending to try to alleviate some of the congestion on 295. We have a lot of agencies that use these tools for what's called after-action reviews. So imagine you have a really big collision or some catastrophe that happens. You then want to go in and you want to run a few reports that tell you how well you responded to that incident or what the impacts were to the public. So here's a crash that happened on a big bridge that goes from Maryland into Virginia. You can see it blocked, pretty much the entire road for a while. The agencies using our tools, they did a diagram of the road on the day in which the incident occurred. And they could see, here's the location of the incident, here's the congestion backing up a solid 6 or 7 miles on this particular roadway. And you've got rubberneckers on the other side that are turning to look and are slowing down traffic in the other direction. They also did a comparative speed map. So they looked at what the speeds and travel times looked like on the day of the collision compared to the prior day of week, just to see how much worse things were. Then they used the user delay cost tool, and they compared normal delay on this road would have been about $150,000 per day. During the day of this collision, that user delay cost went up to $1.2 million. So just looking at these numbers right here can help the agency to justify a change in some of the policies that you might have in the state. So maybe you have a weird towing policy in your state that says, you cannot tow a car until the driver says it's okay and the medical examiner shows up or whatnot. Well, if you're saying that there's $1 million cost of delay here, now maybe you can justify bulldozing a $30,000 car off the roadway for the greater good of the rest of the public, and things like that. I'm not saying that's what we should do, but that's a potential policy change there. We also have agencies that are using our tools to give information out to the public about holiday travel. So you could go back for Thanksgiving and you could show people what normal Tuesday traffic would look like in the month of November compared to the Tuesday before Thanksgiving at the same time. You could show them how much worse traffic is during those days. It's kind of like public information campaigns. We've also given people tools that allow them to produce essentially traffic forecasts. We all watch weather reports every now and then. You see someone standing up and saying, well, on Tuesday we expect this, Wednesday expect that. Well, using our tools and this little visualization, you can actually give people a travel forecast for the holiday week, telling them when they need to avoid the roadways. This stuff is really easy to do, and it makes the DOTs look a lot better, right? Most DOTs are kind of reactive instead of proactive. Well, imagine, the press you get when they put something like this out. Did anyone go see the eclipse, the total eclipse that happened last year? Nobody? Bummer. It was awesome, but there was a lot of traffic that resulted in it. So this is a congestion scan of I-95, Interstate 95 in South Carolina. This right here, well, this is 190 miles of I-95 going through South Carolina. This is 2 Mondays before the eclipse. See, there's essentially no traffic. There's a little bit of traffic right there. This is 1 Monday before the eclipse. And then this is the Monday of the eclipse. As soon as the eclipse ended, which was about 3 p.m., you can see the queue started backing up 90 miles on this road, a 90-mile traffic jam on this one road. And that doesn't even, I just didn't want to keep going into another state, right? It keeps going. And it lasted from 3 o'clock until 10 o'clock. It might have gone even further than that. I couldn't see it from Maryland. I drove down there to see it. I was part of this problem. We also used our tools to go in and generate an animated map. So you can do this from the Probe Data Analytics Suite. The red zone here, that's where you could see the total eclipse. This black moving across, that's when the partial eclipse starts for each part of the country. Here comes the total eclipse moving across the country. Now what you're going to see is after the total eclipse passes, you're going to start to see, especially when the partial eclipse ends, you're going to see all these areas in here becoming extremely congested. People trying to get the hell out of that area, and especially down here in this zone, which is one of the most popular locations. You can see how bad the traffic got right there, and that's all from people going to see this eclipse. And this graphic took all of 15 minutes to put together using these tools. Simple stuff, very powerful in communicating to your clients. So I mentioned it earlier, but New York City has purchased the rights to some of these tools and data from INRIX, which means that if you all are doing work for the New York City Department of Transportation, you can likely get access to these tools to help you in your research, if you think they'll help you in your research. We do offer free training classes, overview training classes. This is the website right here, and we'll make these slides available to you all as well. But feel free to go and register for these. And it might take you a little while to get access. We just have to have someone at the DOT send us an email, say, yeah, we're working with Professor so-and-so, yeah, happy to give you access. And then we can turn it on for pretty much everyone in your research group. But I think that's probably about all the time we have for today. I appreciate you all sitting around and listening to me. And if you have any questions, I'll stick around for a few minutes. But otherwise, thank you very much. Yes.
At the beginning where you had the lane, the incident in the lane closure?
Yeah, the timeline.
You're getting that from probe information? Or?
So for people online, he's asking about the incident timeline I was showing earlier and the lane closure. We are not getting that from probe data. That is getting multi-sourced from different agencies. So the responder data would be coming from like computer dispatch systems.
What type of an incident report?
Yeah, well, they generally do that in real time, like when they're calling out and dispatching people. The lane closure data is coming from the traffic management center. So the operations groups, they're typing that stuff in. Now, there are some probe data providers that are giving you per lane congestion data, but not blockage.
They have the per lane congestion data, they have the granularity to do that?
Some of them do. Some of them claim they do. Yeah. You see it more like on ramps and stuff like that. They'll show you a ramp backing up into traffic. Yeah. All right. Appreciate you all listening to me. Have a good day.
Oh, okay.
Oh yeah, I was stuck in Claremont.
Thank you.
I saw like.
Yes.
My name is Diego.
Hi, Diego.